Hi. Yeah. So, hi everyone. So today I'll talk about interacting fields at special infinity. This talk is based on this work we have done with Anupam, Athira and Shubhrat. So let me tell you why special infinity is interesting. This is because of holography. Like there is this principle of holography of information which says that in any quantum gravity theory, the information in the bulk is already available near the boundary of the Cauchy slice. The massive particles in flat space, the massive particle in flat space, they actually go from I minus to I plus, but these I minus I plus, they are not natural for holography, but whether the I0, the special infinity, it is the boundary of Cauchy slice and it's a natural candidate for holography. But what I consider is actually not I0, but I hat 0, the blow up of special infinity. We take the de Sitter slicings of the flat space, the red lines, these are like de Sitter 3 slices, and the de Sitter 3 slice as at rho tends to infinity, here marked in the blue line, is the I hat 0, or the blow up of special infinity. So we can study quantum gravity theory, but before that we can study just this quantum field theory at I hat 0. This massive scalar field, it has a fall off, exponential fall off as e to the power minus m rho at rho tends to infinity or at I hat 0. Now this, what we can do, we can just strip off this exponential fall off and define an extrapolated boundary operators z tau omega. We have to also smear these operators with a particular smearing function to make the two-point function well defined, which was noted in this paper by Ladda, Raju et al. Now let me come to the interacting field theory. Now for interacting field theory, we choose wide band perturbation theory rather than the usual time-ordered perturbation theory because we are also smearing over time. The smearing function has support over time also. And what I find that the interacting wide band correlators, they actually can have some slowly decaying parts than e to the power minus m rho. So when you are multiplying the exponential factor, you may think like this is diverging. But this, we have a solution for that. What we propose that first you extract the on-shell part of the bulk Weidmann function before taking the rho tends to infinity limit, and this has the correct extrapolated limit. So we only take the Weidmann functions where all the momentums, the k1 and kn, they are on-shell, and this can be actually done in a single Heisenberg operator level. We can extract out the on-shell part of the Heisenberg operator as phi plus and phi minus. The smeared field can be written in terms of them. Now, one remarkable thing that we got, that these operators at I hat 0, the phi plus and phi minus, they can be related with the usual in and out operators. The A and A dagger and B and B dagger are the annihilation creation operators at I minus and I plus, and our operators phi plus and phi minus, they are just average of them. And with this relation, what we find, like these special infinity correlators, they can be actually represented within the class of asymptotic observable found by these people, Caron Holt et al. And so this fits into this story. Now, I want to show some sample calculation for 4-point and 5-point functions. The special infinity correlators, they can be actually written as a polynomial of S matrix and its conjugate, like S star. Here it is written in terms of T. T is just related with S by S equal to 1 plus IT. And here are some possible outlook of our program. So this what we did just free field theory, sorry, interacting field theory, but we can couple gravity with it. We can study for asymptotically flat space, and we can, it is an open question whether we can recover holography from it. And also maybe there is some relation with the celestial shift amplitudes and our correlators. We can also bootstrap the correlators at I hat 0 and derive the consequences about bulk theory. And also there is some recent understanding of S matrix by this TFR group. It would be nice to relate our story to within their formalism. Thank you a lot. Okay.